Hello, everyone, and thank you for joining us today for our webinar, MRI Capital Planning Fundamentals. My name is Dan Kuzneski, Vice President of Global Marketing for Metrosens, and we are excited to have you with us for an hour of your day today. Before I turn over the controls to Toby Gilk, our presenter, let me run through a few housekeeping items with you. For those of you who are not familiar with Metrosens, we're a leading provider of advanced magnetic detection systems, and one of those applied areas are for MRI suites. With our FAROGuard screener for patient screening in Zone 2 and FAROGuard Assure for entry control in Zone 3 before the magnet room, our solutions are enabling safer environments for all clinical staff and patients. To learn more, visit us at metrosens.com. For those of you that are new to Metrosens webinars, allow me to quickly review your webinar console in front of you. In the upper left is your media player, providing guidance on the number of minutes that have transpired. In watching this timer, I'd like to remind you that today's webinar is planned for 60 minutes. In the bottom left is the Q&A window. We will have a Q&A session at the end of the presentation, so please make sure you submit your questions and we will do our best to answer as many as possible. In the middle of the screen is your slides window, which will display the slides during Toby's presentation today. To make the window larger or smaller, click on the minimize or maximize options in the top right corner of this slides window. In the upper right are valuable resources referenced today during Toby's presentation. Please take some time to click these links and bookmark the pages in your browser for future reference. In the bottom right, you will find Toby's bio and links to follow him on Facebook, Twitter, and LinkedIn. Lastly, on the bottom of the screen are icons correlating to each of the modules just described and on your screen. Simply click an icon and that module will disappear from your view. Click the icon again to bring it back. That now takes us to the end of the do's and don'ts, so without any further delay, let me turn the controls over to Toby to talk about MRI Suite Capital Planning Fundamentals. Toby?
Thank you very much, Dan, and welcome to MRI Suite Capital Planning Fundamentals. My name is Tobias Gilk. I will be your presenter for this presentation. A few things about me. I am my day job, I am an architect with RAD planning, radiology planning. Specific to my MRI and radiology facility planning credentials, I am a member of the Healthcare Facilities Guidelines Revision Committee of the FGI. FGI is the most popularly used design standard for healthcare facilities in the United States. For many states use it as their licensure standard for healthcare facility design. And I was on the committee that writes FGI. The committee is responsible for the entirety of FGI, but I was co-chair of the imaging task group that was responsible for rewriting all of the radiology and nuclear medicine design standards. I'm also one of the expert contributors to the Veterans Affairs VA Design Guide. In 2020, the VA released a updated version imaging services design guide that replaced the previous radiology, MRI, and nuclear medicine design guides and unified those three. I have also served twice on the American College of Radiology's MRI Safety Committee, and I'm a named co-author on the 2007 ACR guidance document and the 2020 ACR manual on MR safety. And I'm principally responsible for the appendix that is the MRI suite design element. Anyway, that's a little bit about me. I just wanted you to understand who's giving you this presentation. Whenever I speak on subjects that have to deal with MRI safety, I include this content disclosure. I am a member of the ABMRS, the American Board of Magnetic Resonance Safety, and while I'm encouraged to talk about MRI safety, I'm prohibited from talking about exam-specific content questions. So this is going to be more general in principles and not specific to the exam, as if you were looking for that. So we're going to cover sort of 5 areas, and we're going to, each one of these really deserves, a focused attention in and of itself. So this is going to kind of be an overview. At the end, I'm going to point you to some resources that might be helpful and describe some things that we have in the works with MetroSense in terms of bringing new additional content to you. We're going to talk briefly about the 4-zone model and the acuity classification scheme. We're going to talk a little bit about quench pipes and quench overpressure protection measures. We're going to talk a little bit about ferromagnetic detection products and placement. We're going to talk a little bit about MRI shielding and illuminating some of the differences between the radio frequency shielding and magnetic shielding and how those may be different than shielding that you experience in other radiology areas. And then we're very briefly going to touch on codes and accreditation standards as they apply to MRI suite design and construction. The first of these is 4-zone and acuity classification. And these are really things that you need to identify and work out before you really begin planning the space for your MRI suite. The first of these, the one that I think really needs to be the first thing that gets considered, is acuity classification. For years and years and years, we treated an MRI like an MRI like an MRI. And if it was in an outpatient imaging center or in a physician's practice or in a hospital, we really turned to the manufacturer of that MRI system to give us a prototype. And we too often copied and pasted that prototype, not recognizing that the clinical and operational needs of that MRI scanner are going to vary depending on the clinical expectations or demands of the location. Putting an MRI that is used by ED patients or ICU patients or post-surgical patients is going to require different infrastructural preparations than one that goes into a physician's office. This table, which essentially describes acuity, patient incapacitations through use of sedation or anesthesia, and the degree of intervention. This table essentially helps to guide us to identify what is the highest classification we regularly expect this facility to support, and that classification determination is going to drive minimum clearances and infrastructural provision for that suite. We have had this everywhere else in the hospital for years and years and years. We just call them exam rooms, procedure rooms, and operating rooms. Non-invasive, minimally invasive, or seriously invasive. And now we're simply applying the criteria we have always applied elsewhere in the hospital to imaging services. So when we look at acuity classification and we shift from class 1, diagnostic only, to class 2, minimally invasive interventional, to class 3, where we're talking intraoperative imaging, we change some of the demands for that space, just like we would if it's not imaging space. If we go from an exam room to a procedure room, we're probably going to have a larger room because we're going to need more stuff and we're going to be doing more to the patient. We may change the medical gas requirements. We may change the emergency power requirements. We may change the HVAC demands, including filtration and air changes per hour. As you define your imaging acuity classification, you prescribe a new set of design criteria. So it's very important to first ask and answer the question about imaging acuity classification. And that's going to drive space needs and infrastructure demands for your imaging suite. Now, the acuity classification is true for all imaging. 4-zone, on the other hand, is particular to MRI imaging. And you may have seen the diagram I'm showing on the screen right now. This is from the ACR guidance document on safe MR practices. This has popularly been misunderstood to be a prototype floor plan that gets copied and pasted. The 4-zone model really is not based on defining every space with a room. The control room is not automatically a zone 3, depending on the layout and configuration of your suite. The waiting room, the patient prep area, it's not the function, it's the risk, really, that drives the zone requirements. So instead of using this, I suggest we use this. This clearly does not look like a hospital. This looks like an MRI scanner room floating out in space. But the thing that I want you to take away from this is that the 4 zones are risk-centric. They are not space-centric. There's one sort of quasi-exception to this. Zone 4, the area with the highest risk, you experience the potential for the greatest risk when you're inside the MRI scanner room. That's when things can go flying at the magnet with greatest intensity. So we define Zone 4 as the region within the walls and ceiling and floor that bound the MRI scanner room. And then zones 3 are areas where there are potential MRI-specific hazards. And then zone 2 is where there aren't, the first area where there are not MRI-specific hazards, but there is MRI-specific function. And zone 1, actually, to a large extent, is pointless because zone 1 means there is no MRI-specific function and there is no MRI-specific hazard. If that sounds like your bedroom at home or the helipad on the top of the hospital or your city park or the middle of a river, that's because all of those spaces are, in fact, zone 1. No MRI-related function, no MRI-related risk. So this is what I really want you to take away from what the zones are, or what they should be. So, I'm going to ask you about your MRI suites. And so if you've been involved in a capital project, installing a new MRI scanner or building new facilities for an MRI scanner since the year 2000, have zones and acuity classifications been an essential part of every MRI suite you've done? Well, we've done zones, but not really acuity classes. We've done acuity classes, but not really zones. Or every single time we've done both acuity classes and zones, or we've really not done either of them. So click the radio button associated with the best selection for you. Hit the submit button, and we are moving on in 3, 2, 1. All right. Quench pipes and overprotection. This has to deal with the fact that most, but not all, contemporary clinical MRI scanners use cryogens and use enough of them that we need to have escape pathways if there are specific types of failures of the MRI equipment that release the cryogens. So quench pipes, again, most but not all modern MRI scanners are superconducting, which means they have to maintain super cold temperatures for the conductive elements that we use in superconducting magnets today. Most of these are kept cold with liquid helium. When helium goes from its liquid state, which is about 450 degrees below 0 Fahrenheit, to its gaseous state and warms to room temperature, then that helium has an expansion ratio from 450 degrees below 0 to 70 degrees room temperature of 750 to 1, approximately. Most superconducting MRIs in use today have a significant volume of liquid helium on board. And these require quench pipes, which function kind of like chimneys. In the event that the helium expands beyond what the MRI scanner can accommodate, that helium essentially flushes out the chimney pipe, a quench pipe, to the outdoors, where it can be safely discharged. Some contemporary superconducting MRIs use extraordinarily small, by comparison, quantities of liquefied helium, and they don't require quench pipes. The excerpt on the left is actually from FGI, Facilities Guidelines Institute, and the detail on the right is from a contemporary OEM, manufacturer of MRI systems, with their typical quench pipe design. And I want to point out one particular thing related to FGI design criteria and this quote-unquote standard detail. If you'll note, one of the design criteria talks about preventing ingress of horizontally driven precipitation. If you have a quench pipe detail similar to the one on the right, and this is the discharge end, this is the outside, the exterior part of the chimney. If it comes up through the roof, turns 90 degrees and discharges horizontally, it really can't prevent the ingress of horizontally driven precipitation. It really only takes a wind speed of about 25 miles an hour to drive rain at enough of an angle that it will enter, or can potentially enter, the mouth of the discharge of this quench pipe. Once it gets into that quench pipe, where does it go? Down. What tends to be at the very bottom of a quench pipe? Your MRI system, which means a detail like this has the potential to accumulate water at the MRI scanner inside the quench pipe, which can be bad. Why can this be bad? Because if pressures build up enough inside the MRI scanner, you will get massive pressure discharges, if everything works correctly, out the quench pipe. This picture, which you can't really see, is an MRI in an outpatient imaging center that lost power due to a storm, and the building was storm damaged, and the MRI inside quenched. And that big white plume, that cloud that you see coming up, is cryogen, liquid helium escaping. You actually don't see the helium gas. What you're seeing is, because the helium gas is so cold, you're seeing the water vapor condense and form a cloud, form snow. And so this is frozen water vapor that is rising up because the helium is buoyant. It's lighter than air. It's carrying this water vapor, frozen water vapor, up as it goes. The force of the ejection of helium gas can be really significant. which is why it's really important that we design the discharge parts of a quench pipe as safely as possible. If an MRI has a quench pipe, there are several things that the OEM typically wants to see. They want to see an overpressure relief mechanism. This may not be a minimum design standard in the manufacturer's sighting diagrams or designs or sighting guide, but it is recommended in almost all cases where we would otherwise have a quench pipe. If cryogenic gases, liquefied helium, turns to gas and escapes into the MRI scanner room, we have some pretty significant risks to patients and or staff. There is temperature and asphyxiation risk. The increasing volume of the gas will positively pressurize the room. If we don't have pressure relief mechanisms, it can actually jam the door in the closed position and prevent escape out of the room. The pressurization in some instances gets so intense that it's like inflating a balloon inside the room. It actually begins to separate walls from ceilings. The pressure essentially stretches the interior of the room and causes damage to it. And in the most extreme cases, if this pressure doesn't get out of the MRI scanner, it can actually explode the MRI scanner. Now, this is an image, and I've blotted out the details that would indicate the MRI manufacturer, because that's really not important. This risk is consistent across different MRI vendors, different MRI systems, where there's enough cryogenic material on board that requires a quench pipe. What happened in this instance is, remember that quench pipe discharge detail that prevents horizontally driven rain? Well, this site had one that looked very much like what I was advising you not to do. And what we believe happened is water got in, and they actually had just filled this MRI, topped it off with 1,500 liters of liquid helium, or topped it off to close to 1,500 liters of liquid helium, and that froze the accumulated water in the pipe. When the magnet pressure increased and there was no mechanism by which it could relieve that pressure, it built and built and built inside the MRI scanner until it went kablooey. Very important to design quench pipes and overpressure in accordance with guidance from your manufacturer. And if your manufacturer has one of those up through the roof turn 90 quench pipe details, you may actually want to do something a little bit better than what they suggest. So, are zones and acuity classifications part of every MRI suite you planned? Okay, all right. Not really surprising. Thank you, everyone who responded. We're going to have 2 more audience participation questions, starting with another one right now. Have you ever used an old quench pipe or a design from a previous installation for a new MRI installation? And I'm asking this question both of designers and of sites. If you are an MRI site, a hospital, and you had your MRI replaced, did you just accept that a quench pipe is a quench pipe is a quench pipe, and the fact that there was a previous one should be good enough for this new one without necessarily having it checked and validated? So, have you ever reused a quench pipe or an older quench pipe design? Yes. Why reinvent the wheel? No. New quench pipe for every new installation, or minimally a review and reapproval of an old design. Or if you haven't had to face this yet, click the third one. Now click submit when you've selected your answer, and we're moving on in 3, 2, 1. Thank you. Here we're going to touch on just a few slides, and this is a more involved topic, but I'm going to hit on some of the highlights of ferromagnetic detection products and placement. And I've made up a mythical quote here. Everybody uses ferromagnetic detection the same way, right? I can just copy and paste what I've seen at other facilities, can't I? Well, you can, yes, but that wouldn't be my suggestion. Ultimately, your choice of ferromagnetic detection products and where you place them should be driven by your goals. Are you interested in finding the stuff that patients may be wearing or carrying on them that they didn't take off if you have them change, or you scan them in street clothes and you just want to make sure that they're not bringing their rodeo belt buckle into the room? Are you interested in the same question, but instead of patients, we're asking it about staff, maybe transport, maybe anesthesia, maybe somebody else who's accompanying a patient to MRI? Are you interested in finding implants, devices, foreign bodies that may be within the patient but weren't disclosed on the patient screening form? Are you really concentrated on stopping the big uglies, large projectiles flying into the magnet room? Or are you interested in establishing a ferrous-free working environment? Depending on what your goals are, they may describe different ferromagnetic detection products and different placements of those products. So here we have a prototypical MRI suite. This is actually something that we've taken from the Architect's MRI Siting Guide for MetroSense, and the URL is here. It's also listed as a resource. So here we just have an MRI suite. There are 3 sort of standard locations and 2 different ferromagnetic detection formats that I want you to consider for each project. There's the doorway systems that most MRI suites that have ferromagnetic detection put the doorway detector system on. And this is vitally important. However, we need to recognize that while sometimes they do catch the smaller stuff, the doorway system's real job is to find the medium and larger projectile-related threats. So if ferromagnetic detection systems are designed to screen patients, well, maybe we should have one in conjunction with the patient changing areas. And once we have the patient changed or prepped or put their belongings in a locker, we do a QA/QC with a screening ferromagnetic detection device in the patient changing area. If it turns out they have something, we can then have them put it in the locker right where they're at. But you notice in this layout, we also have a quote-unquote back door or a staff entrance or inpatient entrance into the MR control room. We have a way to circumvent that screening function if you come in the back door. So if we have a ferromagnetic detector here, we can provide ferromagnetic screening for patients or staff or visitors or whomever wouldn't normally come in through the mechanism or the route where we have the screener for patient screening functions. Depending on your use, depending on what you're looking for, there are different ferromagnetic detection products, and there are different ways to locate them so that they serve the needs most effectively. Here we just have a couple of photos that illustrate the 2 standard different formats, the screener single pole system on the left and the doorway type of system on the right. You'll notice that in this case we have the doorway swinging into the magnet room. For those of you who have been taught that for quench protections and entrapment protections, you should never do that. The fact is that with a latching door, outward swinging doors really aren't much of a protection anyway. Swing the door whatever way you want, and relative to the last section, include overpressure relief protections. That way you have the flexibility to swing the door whatever works best for you. In my opinion, in most cases, swinging the door into the magnet room, as shown in this picture, tends to be the better, all things considered. So, have you ever used an old quench pipe or an older design for a new MRI installation? Yes, I invent the field. No new quench pipe or new design evaluation. I have not had to face it. Okay. Thank you very much for answering this one. These are really interesting. We have one more audience participation question, and get your fingers ready. And final audience participation question. At my site, or the last site that you planned, if you're an architect, engineer, equipment planner, we have select all of these that apply. Click on the first one if you have placed a ferromagnetic detector at the magnet room entrance. Click the second radio button if you have placed a ferromagnetic detector in zone 2 as a part of the patient prep function. Or click C, the third option, if you didn't put in any fixed ferromagnetic detection system at all. You didn't put a pillar type of system in at all. Select your answers, and I'll give you 3, 2, 1. Make sure you hit submit, and we're moving on. Let's talk quickly about radio frequency and magnetic shielding in MRI. One thing to note is that if you're familiar with other areas of radiology as a designer, as an equipment planner, if you're familiar with CT or X-ray or fluoro, the first thing you need to know is that the most requisite element of MRI shielding is nothing like shielding in other areas in radiology. Nearly every clinical MRI, there are some exceptions, but nearly every clinical MRI system requires radio frequency shielding built into the walls of the room. It is, when done correctly, it is a 6-sided uninterrupted box. Lead shielding for X-ray or CT may only need to go up to 7 feet and then nothing in the ceiling. That is not the case in MRI. The reason that we use radio frequency shielding in MRI is we are trying to keep radio frequency signals out of the room. Elsewhere, when we're dealing with ionizing radiation in X-ray, CT, or nuclear medicine, we're trying to keep the harmful material, the ionizing radiation, from spreading into other parts of the building. We're trying to keep it from going out. Radio frequency shielding does the opposite. We're trying to keep things from going in. All penetrations into the room, every pipe, every duct, everything that enters the room has to pass through a waveguide, which is a special shielded penetration into the MRI scanner room. Radio frequency shielding is frequently made from either copper or galvanized steel, but any electrically conductive material can potentially be a radio frequency shield for MRI. This is nothing more than a visual aid to show you a couple of different forms that radio frequency shielding can take. The one on the left that looks like you're inside a copper Jiffy Pop, you in fact are. You're inside a copper enclosed room. Walls, ceilings, floors, doors and windows get special treatment to make sure that they are radio frequency shielded as well. On the right, you're seeing a panelized system, and then the green pieces in the middles of the panel are actually sound attenuation that help reduce sound transmission from the MRI scanner room to other spaces. Again, just a visual aid. Magnetic shielding, in many instances, can be avoided if we appropriately plan the MRI suite. not in all instances, but in many. Magnetic shielding is not requisite for every MRI site, but we may need it for a particular reason, and it is the shielding that can act more like what we expect or experience in other parts of radiology for ionizing radiation shielding. Magnetic shielding can prevent, say, a 5-Gauss line from originating from the MRI scanner pushing into an adjacent space. It can also prevent external electromagnetic interference from disrupting the MRI. We can apply magnetic shielding to just one wall or the floor, and we use plate steel for magnetic shielding. We want to try and minimize this or avoid it because the steel, number one, it adds cost, it adds structural weight, but it also can interfere with the effective balancing of the magnetic field of the MRI. And MRIs depend on very precisely balanced magnetic fields. The more magnetic shielding we have, the more difficult rebalancing the MRI can be. So to illustrate magnetic shielding, I found the most over-the-top example that I could come up with. This is magnetic shielding. I think this is for CMRR's installation of like a 10 Tesla MRI. What you're looking at in that sort of barn cross-section shape, that's a plate steel, like 1-inch thick plates sandwiched on top of one another. So you're looking at a foot thick, a 1.5 foot thick steel plate. This is for a very high-end research magnet. This is not what you're going to find in clinical MRI. Again, with clinical MRI, we can apply steel to, one wall, one ceiling, floor, what have you. When we start applying steel in significant thicknesses, it runs the risk of distorting the magnetic field from the MRI. There is actually the potential that if, for example, if we really had to shield the left wall of an MRI room and we were throwing lots and lots of steel at it, the magnetic field from the MRI would be attracted to the left wall and all of the steel in it. We might actually need to put a bunch of steel in the right wall just to compensate, not that we need to shield the right wall. So siting MRI equipment becomes really important to make sure that we follow best practices for siting. Generally speaking, if you're squeezing the room to make it less costly to build, and then you wind up having to add magnetic shielding in to contain a magnetic field, you're probably at least as well off making the room bigger to contain the magnetic field. From a cost standpoint, plus you may be also improving the performance, the clinical performance of the MRI by not having the distortions or the interference effects of the ferromagnetic shielding material. Magnetic shielding cannot be avoided in all instances. There are sometimes you simply have to use it. My recommendation is to try and figure out if at your installation you can avoid it before you commit to using it. And results of a previous poll question. At my site, or the last site you plan, we have used ferromagnetic detectors at the magnet room entrance, in the patient screening area. We haven't used any fixed. All right, things are getting better in the world. I'm pleased by this. I still think we need to ask ourselves the question about what function do we wish to achieve, and make sure that we have ferromagnetic detection systems and placements that really meet that function. Thank you for answering those questions. Codes and accreditation requirements. This is going to be super quick because your mileage may vary. You may be subject to different codes and standards than the ones that I'm going to describe here. I am going to suggest that every MRI suite should be designed based on FGI 2018 or later. That includes the acuity classification codes. I'm going to suggest that every MRI suite should be designed based on the facility performance criteria in the ACR 2020 manual on MRI safety. And I'm going to require of my designers and of facility planners and radiology folks, make sure you understand what your accreditation, which may be Joint Commission, TJC, maybe ACR, American College of Radiology, maybe other organizations. Make sure you understand both the explicit and implicit expectations of design requirements from your manufacturer. There are resources. Metrasens offers resources. There is an Architect's Ferromagnetic Detection Planning Kit, a suite planning document, and as I said at the outset, look for forthcoming professional development programs that will explore some of the subjects we've touched on today in greater detail. With that, I'd really like to thank you for your time and attention, and we'll dedicate whatever time we have left to answering some questions. Dan, what do we have question-wise?
Thank you, Toby. Yes, we do have. Thank you, Toby. Yes, we do have some time for questions here. And just as a reminder, if you do have questions, please submit them in the Q&A window. We'll do our best to get to as many as possible. Our first question is, you showed on one of the slides a layout of staff entering directly from Zone 1 into Zone 3 as a quote-unquote staff entrance. Is this even allowed by code? How can staff just circumvent the Zone 4 requirements? Why would any Department of Health agency approve this? So,
yes, we have seen it done a number of times. I have done things similar to this. It's important that if you do have a staff entrance, if it's staff only, that you are essentially limiting access for people who can badge through that door or have a key through that door. You limit the access to people who have MRI safety training, who are personnel in that department. If we have a technologist or a radiologist, it's really not essential for those individuals, because of their training, to go through the waiting room and the changing room area and the patient locker area, because their training will essentially perform the function that screening process will have done. So if it's exclusively a staff access point, it represents no substantive risk or reduction in the 4-zone protections. If it is an inpatient access way, so you're bringing not only staff, but you're bringing inpatients, that is beneficial in one respect, that we want to segregate inpatient from outpatient populations. So the patient with a vent and 6 medication pumps isn't parked next to the person who's coming in for their suspected ACL tear. You want to segregate those populations. If that quote-unquote back door is an inpatient access, you want to be able to provide the functionality of screening review and a holding area. It can be functionally a Zone 3, Zone 2, Zone 3 alcove off of the control space that accomplishes those functions. So no, a back door, a staff door, does not violate the principles of the 4-zone. And in fact, you can use this for inpatients also if you make sure that the operational needs of that 4-zone model are being met. So that's a really great question. Somebody was being very attentive looking at the diagram.
Great, thanks, Toby. Another question. Can you talk about blowout panel? Was that a blowout panel in the MRI entry door? I usually do it at a sidewall. Can you just talk about blowout panel and why it's required?
Okay, so for those of you who may not have heard the term blowout panel is one mechanism of overpressure relief. So think back to that picture of the MRI that was exploded inside the room, right? If we release a lot of pressure, a lot of helium gas that is warming and expanding and creating pressure, if we release that into the room, there's the potential that we can cause damage to the room. If we don't have a way for that pressure to escape, then people might be entrapped inside the room if the quench happens when you have patients or staff inside the room. So what all superconducting MR manufacturers, if their MR system calls for a quench pipe, they pretty much all universally also recommend an overpressure relief system. And this is essentially an opening inside the MRI room to the outdoors, to an adjacent space where if there is a pressure buildup, you can allow that pressure to escape so that the room doesn't positively pressurize, you don't run the risk of entrapment, that sort of thing. This is in addition to any exhaust fans that serve that area. You can achieve overpressure relief through a few different mechanisms. My personal preference is to do it through a ducted system. Take it up from the ceiling, run a duct to the outdoors with some pressure dampers, and you allow any overpressure inside the room to essentially discharge to the outdoors. If your MRI is buried in the middle of the building, you may not have a good path to the outdoors, and so in that case, you're doing an overpressure relief to other potentially occupied spaces. When you do that, you can do that the ducted way that I described, coming up out of the ceiling, or you can do that with a hatch or a doggy door that essentially allows somebody either automatically or manually to open up a panel in the wall or a panel inset into the radio frequency door and allow the pressure to escape. When that pressure escapes, it is likely going to escape with a bunch of helium gas involved, which, depending on the volume, is a potential safety risk. My preference, therefore, is to do the ducted, both if we can get the duct to discharge to the outdoors, but even if we can't, if we have to duct it into a shared interior space, at least then we're discharging the pressurized air with the helium gas, discharging it at an above ceiling level or at ceiling level. And that helium gas, even when it's super cold, is going to be lighter than air and it's going to want to float. You put a doggy door down at the bottom of a door, between the control room and the scan room. If that scan room pressurizes and starts pushing helium gas out into the control room, after it gets into the control room, yes, it will seek to rise up, but essentially then you're floating this helium gas through the occupied space, through the breathable volume of air that the techs occupy. So it's better, I believe, in the grand scheme of things than leaving somebody entrapped inside the room to have this. But the best of all possible solutions is to discharge that pressure and that helium gas in a way that it doesn't put other people in jeopardy as well as whoever's trapped inside the room. I hope that helps.
Great. Thank you so much, Toby. Another question, and first, thank you so much for your presentation. But followed by, do you foresee a rise in the usage of FMDS and MRI suites? We haven't seen much of them with our clients in Canada in the past few years, and wondering if this will be driven by formal standards or simply good practices.
Well, it should have been driven by good practices for some length of time now. But we are also seeing it adopted in codes and standards. Since, I believe, the 2010 or 2014 edition of FGI, ferromagnetic detection has been a requirement. FGI is a new facility design standard or a renovation design standard for hospitals and healthcare facilities. So because it's new construction or new equipment, it's only forward-looking, which means unless and until your jurisdiction adopts FGI, and even after, once they adopt the FGI, then all new construction from that point forward, in theory, should have ferromagnetic detection. But we have a huge body of grandfathered MRI scanners and MRI suites that aren't required under a design code to retrospectively go back and refit with ferromagnetic detection. Obviously, an MRI with a functional life of 10, 15 years, over a period of time, even if it's only a prospective requirement, sooner or later, all MRIs that have design requirements for ferromagnetic detection will ultimately get that. We are seeing hints at accreditation standards for ferromagnetic detection. And I'm speaking specifically here about the Joint Commission. They have a performance improvement requirement in their accreditation standard that says you are to keep track of ferromagnetic materials that cross the threshold of the doorway into the magnet room. Ferromagnetic materials that you didn't prospectively identify and clear for that patient or that person. The only really way to do that is to have ferromagnetic detection. The Joint Commission standard doesn't yet require that explicitly, but I see the performance improvement requirement as sort of dipping the toe in the pool, that I see this as the direction that the industry broadly is going. And yes, I think while it's not an accreditation requirement today, I suspect in the years ahead it will become one.
Great. Thank you so much, Toby. Another question, really a statement, but I'll turn it into a question. MRI zone 4 doors should open out. So if you have a quench, and you have increased pressure in the room because the quench pipe fails, you can enter the room. And obviously, you were showing a slide earlier and talking about in-swing versus out-swing. So this statement was, it should open out. Would you like to comment on that?
Yes, and I owe the industry an apology, really. So I was one of the loudest voices in the late 90s and early 2000s that said, absolutely, you must have an outswinging radio frequency shield door. And at the time when I was so emphatic about that, the most predominant radio frequency shield doors had roller latches. If you wanted to open the door or close the door, you really kind of had to shoulder check it to get it to wedge free from the door frame. But there wasn't a latch. You didn't have to turn a knob or rotate a lever to be able to get the latch to disengage before you opened it. They really were held in place by the friction between the door and the door frame, and that was it. So in that situation where you have positive pressure inside the MRI scanner room, yes, an outswinging door is a great idea. The problem is that codes at least in the United States, made roller latches, the ones that don't actually catch, that don't actually prevent the door from being bumped open. Roller latches were prohibited, minimally discouraged, strongly discouraged, and in many instances prohibited in healthcare institutions. So what that meant is that the standard way that we closed MRI room doors 25 years ago went away. We changed the way that those doors closed, and we made them, or a significant number of them, have regular latches like every other door in the hospital. As soon as you do that, as soon as you have a positive latching door, the positive pressure inside the room no longer pushes the door open. That latch becomes a lock under pressure. When there's significant pressure applied against that door, it becomes impossible or extremely difficult to actually work the latch mechanism. So if you have an overpressure relief system, the doggy door or the ducted pressure relief, then we no longer need to worry about the room becoming pressurized. And if we no longer worry about the room becoming pressurized, then the direction that the door swing is immaterial. So my recommendation for all superconducting MR suites that have a quench pipe is put the overpressure relief system in, and then don't worry at all about the direction of the door swing. Allow it to swing whatever way works functionally best within that MRI suite.
Great. Thank you so much for those clarifying points. It was wonderful. We have a few questions. I'm going to try to group them together a little bit on quench pipes and quench detail. If the quench detail is not good for wind direction range, then what should it look like? And that's kind of coupled with another question of, can a quench pipe have multiple turns?
So I'll answer those in reverse order. Yes, you can have a quench pipe that has multiple twists and turns and bends and that sort of thing. Every MR system manufacturer will give you design and engineering criteria for a quench pipe that works with that particular magnet. The more turns or bends that you put into it, the longer it has to travel in the pipe, the bigger and bigger the pipe diameter will wind up being. You can make it, as long as you want. You can put as many twists and turns as you want. Just recognize that all of those steps, every length, every bend, every turn, will increase the minimum required pipe diameter. So while the pipes coming out, the quench pipe that actually leaves the MRI magnet is usually on the order of about 4 inches in diameter. If you run it a significant length or throw a whole mess of turns into it, you may have a 10-inch, 12-inch, 18-inch diameter quench pipe by the time you get to the discharge point. Obviously, the straighter you can run it, the shorter you can run it, the less likely you are to have to increase the pipe diameter to meet the pressure requirements for that particular MR system. When you get to the discharge point, yes, I strongly discourage that come up through the roof, turn 90, and discharge horizontally type of detail. There are alternative ways of doing that. One of them is, instead of coming up and turning 90, you can come up and turn 180 and have sort of a candy cane top where the quench pipe discharges in a downward direction. There are also standard details from some of the manufacturers where the quench pipe comes up vertically through the roof and then discharges into a cylindrical housing with a roof on it, and that housing essentially redirects the cryogen gas in a downward direction and provides a full weatherhead protection. I would recommend that you look at, if you're doing an MRI installation, look at the quench pipe details from your manufacturer. If your manufacturer proposes a discharge detail that looks like the one that I showed, comes up and turns 90 and discharges horizontally, find a detail from a different manufacturer. Use the engineering criteria from your manufacturer, your magnets, but you can look at alternative ways of doing that termination and discharge. I hope that helps.
Great, and that takes us to the top of the hour, and that's all of our time today. I want to start by thanking Tobias Gilk for joining us today and giving us this presentation. I want to thank everyone who participated and submitted questions. We got quite a few questions, and we will do our best to answer some more of those post-webinar that we were not able to address in our 60-minute time window today. And just as a reminder, this webinar will be available on demand at the same link that you used in order to register for today. And you will get an email approximately 4 hours after we end today with a link so that you can revisit. Thank you again, Toby. Thank you, everyone, for joining, and I hope everyone has a great rest of their day. Take care.
Thank you all.